only thing about evaluating a triple integral, sometimes it's tedious. Sometimes a little tedious. Okay. 2x squared y minus x cubed y minus, what does this become? X squared, I want that chocolate fade. X squared y squared over 2. Okay. And what are we plugging in here?
2 and 0.
2 and 0. And what letter are we plugging them into?
Y.
Alright. I'm going to plug in the 2 there, I get what? 4x squared?
Minus x.
Oh, thank you. So this is a 2 minus x.
2 minus x.
Let me put it right here too. 2 minus x. I can't even write it right now. 2x squared times 2 minus x. Minus x cubed times 2 minus x squared times 2 minus x squared over 2. But then when you plug in the zeros, what do you get? But everyone, I'm excited because we now have this down to a what? A single integral. This is why I put this off to the left. Can anyone read this? I don't want to write it too small. I just knew this was going to be a monster. We're like, okay, get through there. We're now down to a single integral. You want to just distribute all that stuff? Does that sound good? Unless you want to factor. You might factor out at 2 minus x. I'm just going to distribute. It shouldn't be too bad. All right, here we go. What's this all distributed? 4x squared minus 2x cubed minus 2x cubed plus x to the 4th minus, okay, I gotta be careful on this. What is that FOIL? Help me FOIL that out. Good job. 4 minus 4x plus x squared. So I haven't done the integral yet. I just thought let's expand, combine like terms. I feel it'll get a little better. There's like terms in there. Let me write it again. 4x squared minus 2x cubed minus 2x cubed. So far so good? Plus x to the 4th minus, what's that? 2x squared, what's that? Plus, what's 4x cubed over 2? Alright, and minus x to the 4th over 2. And I distribute that, right? Minus, then that was a plus, that was a minus. Good, yeah. Now where are the like terms? I'll draw arrows. Where's all the x squareds? Alright, here's an x squared. What's 4x squared minus 2x squared? I get 2x squared. What's minus 2x cubed minus 2x cubed plus 2x cubed? Minus 2x cubed? And what are the other like terms? Oh, what's 1x to the 4th minus 1/2 x to the 4th? Plus a half x to the 4th? Okay. But check it over. Everyone okay with the like terms? 2x squared, negative 2x cubed, net, plus a half x squared. What's these integrals? Only thing about it is a little tedious. 2x to the 4th over 4 plus x to the 5th over 10. Alright, what's this answer? I get 16/3 minus 8 plus 32 over 10. And I don't care if you do it right now in a calculator, if you don't want to get common denominators. You can write it as a fraction or as a decimal. I'll write it both ways. I don't know how you're going to want to write it. What's that number? What's 5 1/3 minus 8 at 32/10?
I got 4/10.
Pretty good. can do common denominators, but I have to get a common denominator of 30. Right? You'll get there. What's 16/3 minus 8 plus 32 of 10? 8/15. What's that as a decimal?
0.53.
So I'm going to write it both ways. 8/15 or 0.53 is our, not volume, but the mass. You can check it again. I think it was just that 4/10 came out. And then you can do common denominators here, right? Hey, you could have checked this with your TI-84, right? You know, like you got to there and you're like, all right, I'm just going to put that there. That's okay. But please explore. I encourage you to explore some of those, you know, on the internet. If you don't have a CAS at home, computer algebra system, like a TI-89 or a TI-Inspire, because they are a little tedious. This would have been crazier if this was what? Z-squared. Or what if it was Z-squared Y, right? It can get a little nasty. Cool. That's why, hey, again, your next test, many of the problems I say set up. But when you do stuff in polar coordinates, these don't take that long, so you can solve those. Some of these, just set up on. Hey, great job with the tetrahedrons. So now let's look at a problem like this. And can you find the volume? Of the solid bounded by the paraboloid. I had this on your practice problems. I just want to see which problem I'm doing. Oh, I know where I put it. I have it on this one. Okay. The paraboloid z equals x squared plus y squared plus 2. And the plane z equals 18. So we'll find this. Or we can at least set it up. Now, can we draw this? What does that paraboloid look like? This is why these images are important. That's why section 12.6 is important. Can you help me sketch that paraboloid? What does that look like? There's the paraboloid. How high does it get to? 18. Let's keep opening up like this, right? But it's going to intersect the z equals 18 in a what? In a plane. It's going to be a plane, it's going to intersect that plane, but won't it be a circular intersection? Because this is a circular parabola. So that's why I'm drawing it like that. Now this is up 18 notches. This is z equal to x squared plus y squared plus 2. And look at the volume of this solid bounded above by the z equals 18, and then getting bounded below by this surface. This is the bottom surface. The z equals x squared plus y squared plus 2. We're going to get the volume of that solid. Triple integral, right? Triple integral for what? For volume. Volume is mass, we do triple integral of the density, but volume, we just do triple integral of the number 1. Okay. 1. You know, dv and then e, right? Look, dv, this is e, this is e. That's the solid e. We can define that also. That's e. What's the top z then? That's easy. What's the top surface? 18. the bottom 0. We just did 2, maybe 3 problems in a row. I know at least 2 where the bottom was 0. Is it 0? It's very good. I love it. That's the big error in tests. People, you see 0 so often, you're thinking, I guess that's 0. Look what it's bounded below by. By that equation. So I'll put it, what is it? X squared plus y squared plus 2, right? Everyone okay if we project this onto the xy plane? So what number goes here? 1. dv, I'll just put e here, right? Well, now I can just put, this is the projection. But, that's a circle. What will the projection be? The projection onto the xy plane is the widest region ever involved in this solid here. Let me say it again. The projection onto the xy plane is like the widest region ever involved inside this solid here, which we can see is that disk way up at the z equals 18. The only thing is I don't know how big that circle is. You gotta help me find it. And because it's a circle, can't we go what? Polar? Does anyone agree? Polar makes things easier, right? So let's definitely go polar with this. But that means mathematicians had to invent a coordinate system that dealt with polar coordinates in triple integrals. And there's a name for that. That's what I want to lead into right now. And the title of 15.8 is called cylindrical coordinates. Okay? So I'll put it right here. What is cylindrical coordinates? It's polar coordinates with the variable z. How cool is that? It's not too hard. Cylindrical coordinates is basically what we're looking at right now. How to handle this problem. Cylindrical coordinates, first of all, we could say our coordinates would be r for radius, theta, and then what would be the third variable? Z. Everything's in terms of r, theta, and z now. So cylindrical coordinates is polar coordinates with what letter? Z. Does that make sense? Cool. Yeah, we're saying here, I'll do everything in a circle, and then I'll go up straight up. It's like we can think of things as cylinders. But it's so awesome for problems like this, right? Because I can still do a triple integral, but hey, don't forget, we're still going to have to put this what? This r. So you know what this looks like? We're saying a triple integral of some function of what? X, y, and z dv is equal to, let me write this out. I'd say f of r cos theta, r sine theta, comma z, and then what letter again? There's that element, I need it. I need that element. R dz dr d theta. But here, do a little squiggle there or something to remind you, don't forget about that r. Feel free to put that r out in front of this. Okay? Feel free to put that r way out in front so it stands out. Here, I'll put it in yellow. Don't forget about r, like the pirate RDR. RDR. Cool? So let's do this problem, everyone. Go polar. But you know what we're saying? Because it's three-dimensional, go what? Go cylindrical. Go cylindrical on this. I mean, I could have ran out the first integral and got it to polar coordinates, but that's what cylindrical coordinates is for. For problems like this, where these shapes, these projections are circles. Cool? So I'm going to start setting this up. I'm going to go cylindrical. Whoop, whoop, whoop. What's this number? 1. What's the variables? dz, dr, and d theta. Did I forget anything? Way to go, Rich. I'm telling you, everyone, you may laugh, but you wouldn't believe how many times this happens on a test. You get your test back and you're like, oh my gosh, I got an 82. I would have had a 97 if I just didn't forget r in 3 problems. It can get forgotten. Rich says you need an r right there. Because I'm doing volume, but oh. Now, what's the top number? 18. You gotta help me with this. I can't leave the x's and y's, that's Cartesian. Any suggestions? What can I call that? Totally good. R squared plus a 2. Okay, what do you think theta is? We can do the theta. What do you think theta is? Look, this is theta. It's going all the way to around. What do you think theta is going to be? 0 to 2 pi, you bet. So the hardest part is, what the heck are the radii? What's the limits of the radii? It's that, right there we call it the projection. It's that wide circle that gets projected on the xy plane. I don't know how wide the radius is. Now, some of you are probably doing your head, but I say we work it out right now. I'm going to put 0 to 2 pi, but this circle here. What's the radius? How do you find where two surfaces meet each other? Set them equal to each other. We have to do that. We have to go off to the side of the paper somewhere and figure out what's going to be the radius of that circle. So let me just go off there. Where do these two surfaces meet? Where do they intersect? Question mark. And you're saying let x squared plus y squared plus 2 equal to 18. Subtract 2 on both sides. I think you all are going to know the radius of this circle. Is that radius 16 or 4? The radius is 4. Now some of you might have done that in your head, but that's the this is a radius of 4. Gets up to 4, goes down to negative 4. That's called the projection onto the xy plane. That's what they call it. The project. It's way up here, but it's the projection. We have to make sure we hit the widest region ever encountered. So limits of radii. Not negative 4 to 4. R is never negative with these. 0 to 4. And then theta is what? Hey, when it comes to solving it, we don't have to solve it. We set it up. Unless you want to do. The problem in the price sets it set up, so we'll just do setup. You know what though? I want to solve this with you. I was about to say just do the setup. Let's solve this because this does not take long. Remember how long